See if it'll play. Can't hear it, can you? Remember this? What does he say?
Vectors, magnitude, direction.
Direction and magnitude, right? All right, that's what we're studying today, vectors. We're going to finish off our section on vectors. And vectors, like Mr. Vector says, when you think of a vector, which is all you're going to do in mechanical engineering or engineering practically, is vectors, right? Physics is one of the things you can think about. So vectors, when we think about vectors, vectors have what we said, a magnitude and a direction. So for example, when I say that I walked 15 feet to the right, I have a directional vector right there. I pushed up with a force of 80 pounds. We have a direction and we have an amount. The baseball left my hand at 60 degrees at a rate of 90 miles per hour. Those are components, right? You have a direction and a magnitude of the values to create the vectors. Now, scalars is just simply a magnitude, right? It's just it's a scale value is what I always think of it as. So if I have a mass of 200 pounds, I don't have a direction with that. I just have a value, right? The speed of the car was 20 miles per hour. We don't know what direction it was going in. We just know it had a velocity. Okay. I walked 250 feet. I don't know what direction. I just know that I went 250 feet. So that would be the magnitude or the length. So when we think about vectors, how many of y'all are already familiar with vectors? Raise your hands. A couple of you, about a third of you, a fourth of you, right? From physics. Did you take physics in high school? Yeah. All right. So for those of us who didn't have physics in high school, we have, or a refresher for those of you that did. When we think about our vector, what we have here is an initial point and a direction. So we have an initial point P moving over here to the terminal point Q. So we have an angle that we went at basically. And so we have a directed line segment along with a magnitude. Now, a couple of things just for notation here. Most of the time when you see vectors notated in a textbook or something, they're going to be notated by a lowercase letter that's bold. Now I can't write in bold lettering. So typically when we write vectors by hand, we'll write vectors with that like half arrow above it, indicating that that is a vector. Okay. Now, vectors are directional, so they're defined by their direction and they're also defined by their magnitude. So let's start out by just figuring out, well, what is the magnitude? The magnitude is really just the length of my segment, right? The length of my segment. So here, I want to take these two vectors. I have vector U, which you can see originates at the origin. And I have vector V, which is defined on that line segment or that ray RS. Okay, does everybody see that? And I just want to be able to show, we're just going to practice, how do I find the magnitude of these two vectors? In other words, I want to know what the length of the vector is. So when we're thinking about magnitude or the length of that line segment there, the magnitude, which we write as kind of these double bars, I'm going to say the magnitude of vector U is going to be equal to the square root of the difference in my X values. So if I've got my two ordered pairs here for that ray, for the vector U, I would say 3 minus 0 squared plus 2 minus 0 squared. The distance, right? That's the distance formula. Yeah, all right, so this would be 9 plus 4 or the square root of 13. So the length of that line segment, the length of vector u, which is the magnitude of the vector would be square root of 13. That's just the distance formula from way back when. Let's do the magnitude of vector v. It's going to be the square root of, and I'm going to take the distance, the difference of the x coordinates, so 4 minus 1, and I'm going to square it, plus the difference in the y coordinates, which is 4 minus 2 squared. 4 minus 1 is 3, squared would be 9, plus 4 minus 2 is 2 squared, or 4, so 9 plus 4 is the square root of 13. They're exactly the same, right? Okay? So that's just finding the magnitude. Okay, any questions on doing that? Everybody see where I got those values? Okay. Now, when we think about our vectors, we can write them a couple of different ways. One of the ways that we can write them is we can represent them in what we call component form. All right, so if we're looking at, let me scroll back up here for just a second. If we're looking at vector u from above, the problem that we just looked at, when we write that vector in component form, notice that it's not a set of ordered pairs that we're actually looking at. It's these, like, you know, they're not brackets, but they're those things, right? They're the sides of it, all right? And when we write it in this vector or in this component form, what we're basically writing it as is its x direction. How far did it travel in its x direction, and how far did it travel in its y direction? That's what those little arrows mean on either side of it. It's not an ordered pair, it's a vector. So let's practice then, how do I write something in its vector form? It's pretty straightforward, so we're just going to kind of draw our picture to kind of go with what we're looking at here. So I want to write the component form as well as the magnitude of this new vector that has an initial point at 4, -7, so that is an ordered pair, and a terminal point at the point -1, 5. So graphically, let's kind of just sketch what this thing looks like. So if I have an initial point at 4, -7, so I'm going to move 4 in the horizontal on the x-axis, and I'm going to move -7 in the y direction. That's my first point. That's the initial point. The terminal point is going to move -1 in the x direction and +5 in the y direction. So we have a directed line segment, right? I've got a directed line here, sort of. It's moving up in that direction right there. And that's vector v. Now, because I sketched it out, we can say if we wanted to, just graphically, I want to show you what this looks like. If I write it in its component form, I have to determine how far did it move in the horizontal direction. So from its initial point here, down there at the bottom right, I moved 5 units to the left, didn't I? I moved 5 units to the left, which would be a -5. And the vertical component right? The vertical component has to be 7 units back to the x-axis plus another 5 units above that. So I would have a total of how many units in the positive direction? 12, all right? So geometrically or graphically, when we're talking about our components here, this is what we're looking at. Now, how do I find it without actually sketching the picture? So again, if I wanted to write it in its component form, I want to take the x values, right? I want to take the difference in the x values, which would be a -1 minus 4. And then for the y values, I would take the difference in the y values. So 5 minus a -7. So -1 minus 4 plus a negative would be a -5, just like we said above. And 5 minus a -7 is a +12. So I get the same answer, but I've done it algebraically as opposed to doing it graphically. Okay, so to find the x, or to find the components, you're just taking the difference in the x's and then the difference in the y's. Now, how will I find the magnitude? The magnitude we said was the distance of that line segment, okay, which is the distance formula. So we would take the square root then of -1 minus 4, but we square it, plus 5 minus -7 squared. Well, we already know, because we found the components up here, that this would be -5 squared plus 12 squared. 25 plus 144 is 169.
13.
Which would be 13. So the magnitude then of the vector is 13, the total distance. Okay? All right. So this form, like I said, that we're looking at right here with the arrows or the little, what do we want to call those there? What do we want to call those little thingies on the side? They're not parentheses. You don't know. You don't care, do you? All right, well, we'll just write it like that. That's the component form, okay? Now, vector operations. So we can take these vectors and we can perform some operations on these vectors. So generally, we're going to be adding them. You can also subtract them, okay? We can multiply them by a scalar. Do you all understand the difference between scalar multiplication and maybe like dot multiplication? How many of y'all remember doing matrix multiplication in matrices in college algebra? Anybody do that? Yep. Okay, matrix multiplication, you didn't get, it wasn't just straight multiply by a number, was it? When I just multiply my vector by a scalar, which is just a value, let's call it an integer value, or it could be fractional, I suppose, just a number, then I multiply each component of the vector by that same thing. In other words, you're scaling it up or down. That's all scalar multiplication is. We can also add and subtract these vectors, and we do that by just adding or subtracting their individual components. Okay, so the horizontal movements get added together and the vertical movements get added together. Now, graphically, what you've got going on is if I had these two vectors here that you can see on my picture, right? On the left-hand side, I have vector u, and on the and then I have vector v. So I have these two vectors here. And if I put the two vectors end to end, so in this gray picture here, I have vector u plus vector v. Well, I can figure out then what the total sum of that would be, right? Where I wanted to know maybe what the diagonal almost of a parallelogram is, right? That's what that kind of looks like. So that's what we're doing when we're adding them together. So let's just take a couple of these examples. I have vector v, which is defined as -2, 5 in its component form. I have vector w, which is defined as 3, 4 in its component form, and I want to perform the following operations on it. So if I wanted to multiply the number 2 times vector v, then that's just going to be for each part of its component. So I'm going to take 2 times the -2 that was already there, and 2 times the 5, giving me a new vector of -4, 10. So starting at the origin, right? If you picture over 4 and up 10, that would be my new vector. Now let's try then w minus v, vector w minus vector v. So you're going to take the horizontal component of w, which is 3, minus the horizontal component of v, which is a -2. And then you repeat the vertical component of w, which is 4, minus the vertical component of v, which is 5. So I would end up with 5, -1. Do we agree with that? All right, now you do the last one. Do v plus 2w. Okay, do you get an answer? Yeah? What'd you get?
413.
413. Does everybody agree? 413? And that's what those vectors look like when we do that addition. Graphically, that's what they look like. So on the left-hand side, you can see you started out with vector v here in gray. And when I multiply it by a scalar, I just scaled the vector up by power of 2. Okay, here on the second one, w minus v, so I had vector w minus vector v. Notice the direction that vector v is going in the negative direction, resulting in this vector down here at the bottom of that triangle. Graphically, this is what they look like. Here is the last one you all were working on. So I have vector v and vector 2w, and I end up with v plus 2w. Okay? That's what we're doing when we're adding them together. All right, so that's what they look like graphically. Does it feel hard yet? Any of this feel hard?
Yes.
Yes? All right. Let's do some more then. Okay, still basically still working with operations on our vectors. Except this time, I'm going to multiply the magnitude. I'm going to multiply the magnitude by a scalar. So let's look at letter B first. If I have vector u up here, okay, there's my vector, and I am going to multiply -5 times its magnitude. Well, we want to make sure that this negative here, when I multiply it by a scalar, I'm actually going to multiply it by the absolute value of that. So the absolute value of -5 is 5, right? That's what we're going to multiply our magnitude by. So 5 times the magnitude of u. Well, the magnitude of u, remember, is the x component squared plus the y component squared. Or in other words, 9 plus 1 would be 10. So this is going to be 5 times the square root of 10. That is this operation here.
So where did the negative go?
We're going to just take the absolute value of the scalar.
Oh.
Okay. You do then part A. 3 times vector, the magnitude 3b. You get 3 times the square root of 29.
Yes, ma'am. Yes.
Okay. All right. So the only thing you have to remember is when you're performing operations with these and you're doing magnitude, you want to take the absolute value of that scalar multiple. That was the only difference between them. Now, the nice thing about vectors is you can represent vectors all over, right, a Cartesian coordinate, or if that's what you want to think of. But we can also think of vectors as unit vectors. So if I wanted to know what the unit vector was, I can find the unit vector by dividing the vector by its magnitude, basically what it is. We do the same thing if we think about unit values also. You divide that number by its length, I guess, so is probably not a very good example, but that's what we kind of think of in that way. So for any non-zero vector v, the vector v over magnitude v becomes its unit vector. Let's see what that looks like then here. So I have vector v, which we define as 4, -2. And I want to rewrite it in terms of its unit vector. Breaking it down into its very, very smallest part is basically what it is. So we first have to figure out what the magnitude is of v. So the magnitude of v is going to be 4 squared plus -2 squared, or in other words, 16 plus 4 would be
1 squared.
Thank you. Square root of 20, and we'll write that as 2 square roots of 5.
How do you do that?
Okay. So square root of 20 simplifies to be 2 square roots of 5. So when I write this now as v over magnitude v, that looks like our components divided by the magnitude. And we can just kind of separate this out by saying, okay, so now I have the horizontal movement would be 4 over 2 square roots of 5. Vertical movement would be -2 over 2 square roots of 5. Simplifying the whole thing, I end up with two over the square root of 5 plus, or excuse me, 2 over the square root of 5, comma, -1 over the square root of 5. And then if I needed to go one step further, I could rationalize the denominator. So I would get 2 square roots of 5 over 5 negative square root of 5 over 5. So what that is doing in essence is, if this is my vector, represented by that long purple line, then the unit vector says I'm going to move 0.894, which is 2 square roots of 5 over 5. You did that in your calculator. 2 divided by the square root of 5. So I'm going to move in the x direction, 2 over the square root of 5, and I'm going to move in the y direction, -1 over the square root of 5. Those are just the decimal representations. So that's all a unit vector is. It's kind of breaking it down into its very smallest component. Okay? And you just do that by dividing the vector itself by its magnitude. Now, other than writing it in its component form here, we can write it also, there's another way to represent it, and we can write it also using a linear component. Which is also called the IJ, with a little hat, form.
Is that what?
All right, the IJ form, and I got little hats on there. And the IJ form is just one other way for us to talk about it. The I part represents the horizontal movement. The J part represents the vertical movement. And so to rewrite our vector in its unit, our unit vector that we just found, using this new form, it's just going to look like 2 square roots of 5 over 5 I hat minus the square root of 5 over 5 J hat. They're pretty much the same. I mean, they are the same, right? You have how far did you move in the x direction? Well, I'm moving 2 square roots of 5 in the x direction, and you put that next to an I. How far did I move in the y direction? I moved negative square root of 5 over 5, so that goes next to the j hat. It's just a different form of writing it. And so if I were to extend this concept then and say, okay, well, let's perform an operation then with vectors that are in this linear component form as opposed to the other form that we were looking at. So I have vector u, which is defined as -3i plus 8j, and vector v, which is defined as 2i minus j. And I want to know what is 2u minus 3v. So similar to what we did before, I'm going to take for the vector here, let's say 2 times, I'm going to rewrite vector u as -3i plus 8j that I'm multiplying down here. And then minus 3 times my v vector, 2i minus j. Now we just kind of distribute and simplify like terms. So 2 times -3i would be -6i plus 16j minus 6i plus 3j. Collect your j's and your i's and write this as -12i plus 19j. That's the IJ form or the linear component form, as opposed to the other form that we saw a moment ago, which could also be represented as -12, 19, with our little arrows on the other ends of it. Same thing, and pretty much doing the same thing, right? Collecting your horizontal movements together and you're collecting your vertical movements together. So the last thing that we want to talk about then is if we know kind of the length of these vectors, we also have to add that direction to it. So not only magnitude, but also direction. And when we combine those two concepts, right, the length or the component of its movement combined with its direction, we can basically think of our vector as being equal to cosine of theta, because that's our horizontal movement. So it goes next to I, plus sine theta, which is our vertical movement, which goes next to J. So I can figure out what the angle is of my vector. Don't forget that from trig, we know that tan theta is defined as our y over x, right? We've always defined tangent as y over x. So let's see if we can find the direction of u. Find the directional angle for the vector u. So I know that I'm going to move 3 units in the horizontal direction, and then I'm going to move 3 units in the vertical direction. And I want to know what theta is. So I moved 3 along the x-axis, 3 along the y-axis. Well, tangent of theta is equal to y over x, or in other words, 3 over 3.
Which is 1.
Which is 1. And so therefore, what angle, when I take the tangent of it, do I get a positive 1 that's here in the first quadrant? So theta has to be 45 degrees or pi over 4. So let's do the same thing here for this next one. If I wanted to talk about, and that was vector u, if I want to talk about vector v, then I'm going to move 3 units in the x direction and 4 units in the y direction, -4. And I want to know, so this is vector v, I want to know what is theta, positive theta. Okay, I want to know what positive theta is. So how would I do this? Tangent of theta is defined as -4 over 3, correct? Okay, do I know what that value is off the unit circle? So I'm going to use my calculator.
Find tangent of
Okay. Let's do this in degrees.
.023275.
No, that doesn't sound right. Put it in degrees.
It is in degrees.
Uh-huh. So I want to know what did I say, I want to know what tangent is?
Yes.
I want to know what inverse tangent is.
Okay, that's fine, that's it. And it could be 3.13.
All right, so we got -53 because that puts it in the fourth quadrant using our calculator, but I want to know what the positive angle is. Make two.
Here's,
806.87. 306.87. I got a second on that one, Reagan.
What is that, just 360 minus?
here's
360 minus 53.13.
Because it needs to be positive.
So remember, when you get that value, if it's in the fourth quadrant,
Wait,
or if you get, and that would be, well, never mind. Yes, Javi?
no. I'm mistaken. They mean interrupt you, I'm sorry.
Okay. So what do we know so far? We know, right? We want to know how do you find a magnitude, right? How do you find the magnitude? You're basically taking the distance between 2 points. That's the distance formula, okay? We know that we can define our point using, we can define our vector using the vertical and using the horizontal and the vertical values of it, right? Okay, so how far did I have to move in the X direction? How far did I have to move in the Y direction? That's the component form. Okay, we know how to perform operations on it, right? Yeah. Okay, trying to help you think about how you're going to write this down on a formula card. Scalar multiplication, we've got all those, right? Don't forget that if you're finding the scale, if you're doing scalar multiplication on a magnitude, then you take the absolute value of it. All right?
You can scalar multiplication
On just the vector components, you don't have to take the absolute value. Okay? Unit vectors, you're going to take the components and divide it by its magnitude. Okay, you can also represent it using the IJ form or the linear form, right? Okay, it's pretty much the same thing, right? The vectors are pretty much the same thing. And then just remember that the horizontal movement is going to be cosine theta, vertical movement would be sine theta. And then you can always find out what theta is as well, okay? Using tangent of those, using our definition, all right? Let's practice one problem. Okay. So we have an airplane that's traveling at a speed of 500 miles per hour with a bearing of 300 degrees at a fixed altitude with a negligible wind velocity, which you can see here in the first image. I'm just going to read it first. The airplane encounters a wind with a velocity of 70 miles per hour at a direction of north 45 degrees east. And we want to figure out what is the resultant speed, in other words, the magnitude of the final velocity, as well as the direction of the plane. So the angle and the magnitude of the final velocity. Now, a couple of things were already done for us in this problem. First of all, remember that when we are talking about bearing and we don't have we don't have the other notation here, that it is considered clockwise from true north, right? So you're heading clockwise from true north. So they already did the fancy work for us here, all right? And figured out that the resultant angle is 120 degrees. So if my bearing was 330 degrees, then the resulting angle off of this horizontal ends up being 120. All right, I challenge you to try to figure that one out. I'm not going to confuse you with it right off the bat. So we have this angle here. All right, that's how far the plane is flying off of a horizontal, off the horizon, let's say. Okay. And it's traveling with some speed of 500 miles per hour. Now, ultimately, we come down here. If we know that V1 is our airplane vector, and the wind is now blowing at another vector, all right, then it has a resultant vector that we are ultimately trying to find. Okay, so we're just going to be adding those two vectors together to get the resultant vector. So let's kind of divide this up a little bit. Now, we know that we're going to call V1 is the vector that we're going to identify as the plane. And V1 is going to be 500 miles per hour times, so the velocity basically is 500 miles per hour times its vector component. Now the horizontal movement for V1 is going to be cosine times theta, right? Because we defined that as our horizontal movement. So it's going to be the cosine of 120 degrees. And the vertical movement of that vector is going to be the sine of 120 degrees. So far, so good. I just am going to multiply how fast it's going at that direction. Okay? And it is traveling at a direction of cosine times 120. That's it's in the x direction, and sine 120, right? Those two components make its direction. So V1 is going to be, to one decimal place, y'all tell me what the horizontal and the vertical components would be.
-0.5 cosine 20.
Times 500.
-250.
Okay, negative 250 for the horizontal, and then what do we get for the vertical?
33.01.
Do we agree with that? Yeah, okay. Now, let's take V2. V2 is what we're going to identify as the wind. Now, in the problem, it says that the wind is traveling at a velocity of 70 miles per hour at a direction of north 45 degrees east, right? Okay, so that means that we do 70 times the cosine of 45 degrees, because that would be northeast 45 degrees. That means that the angle theta would also be at 45 degrees, wouldn't it? Okay, so cosine 45, sine 45. We only said one decimal, what did we say, 2 decimal places?
Yeah.
All right, let's do it to 2 decimal places again.
Would be nine.
49.50.
For both of them, right? So the last, well, sort of. So now the vector, the resultant vector of the plane's speed along with the wind would be V1 plus V2. So the component form of that is going to be what?
Plus 49
Yes, sir.
plus 49. Add
I
those.
mean, 433.01 plus 49.50, right? I'm adding the vertical components together, and then I'm gonna add, excuse me, I'm adding the horizontal components together. Negative
Well, I was
250.
correct when I said- I said 250, not negative 250.
Oh, I got you. All right, so what do we get for the horizontal component? And then what do we get for the vertical component? So the question says, I want to know what the resultant speed is, which is the magnitude in that direction. Okay. So I need to figure out what the magnitude is of the vector. We know how to do that. That's the distance formula, right? Okay, so what is the value of, what's the magnitude of this vector? It's just going to be the x component squared plus the y component squared under the, and then take the square root. What do we get?
522.31.
Okay, so 522, did you say 0.3?
0.31.
All right, so we'll say 522.3. That's how fast it's moving in the direction that it's going.
Mine says 522.5.
My answer key says 0.5, but I wasn't sure. All right, Sam, you're,
Oh, I forgot to put the 0.5 on one.
so we have now the speed that it's traveling, and now I want to know, the angle it's traveling first. How do I find that directional angle? It's the inverse, it's the tangent of theta would be equal to the y component over the x component, right? So tan theta is 482.5 over negative 200.5, or in other words, theta is going to be inverse tangent of that, right?
And theta be negative 67.6.
Okay, so your calculator returned for you negative 67 point, I got 44.
Well, mine says 0.64.
I don't know, which one is it?
Okay.
44? 44, okay, we're going 44. So we know that the calculator returned for us this angle down here, right? In the fourth quadrant. Okay. What is the angle then in the second quadrant? right? How far, what is theta then in the second quadrant? That would be 180 minus 67.44, correct?
112.56. Yeah, that sounds about right.
112.56. That would be theta up there in the second quadrant. Okay, that's the same thing that we've been doing, right? When you use your calculator, it's going to give you that value. And we know that we're up here in the second quadrant because we drew a picture and we can see we're up there over there in the second quadrant. Now, the catch to this is that it actually says, I want to know what the true direction of the airplane is. In other words, I've got to adjust this angle for its heading or its bearing. So if I have, so this is theta. That was the theta that we just calculated, correct? But I want to know what that measurement is, because that's how we come up with the heading like what we started with, right? True north, you rotate clockwise around. Catch to this is this value here is 67.44, correct? The value from the horizontal axis up to my green line, you agree with that? Remember, that was our reference angle that we found over here. This value right here, in other words, is 67.44. Do we all agree with that? That would be the reference angle. You see that? Yes? So then the true direction is going to come from 270 degrees plus the reference angle of 67.44, which is 337.44. All right. So the true direction came from that right there. Okay, that's the value of the true direction. All right, vectors. Have fun with them. Y'all are gonna see them forever in physics and forever everything else. That's your life right there. That right there. Welcome to engineering, because that was all I saw my son do all weekend long. Statics and dynamics, physics. Not a word problem like that.
Okay, but like this.
Vectors and really says.
Probably adding or subtracting vectors, right? Something like that. Write down the formulas that I was trying to go over with y'all, right? Understand how to find the magnitude. Okay. All right. Your test is about 20 questions long. Because that's about all the time that we have, right? It's about 20 questions long. It's going to cover, it covers all the identities that we've done. So that includes performing operations on identities, right? So at the very beginning of when doing identities, we were adding them and subtracting them. How did you add and subtract? Not necessarily the identity, but how did you add and subtract two things? You had to have a common denominator, right? Okay. Performing an operation like factoring or multiplying them and then simplifying them, right? Okay. Verifying identities, all right? You're going to have to verify an identity or two for me. Solving equations. We've been practicing solving an equation. Then utilizing the rest of the identities that we were doing this past week, where we were talking about the sum and difference identities, the half angle identities, the double angle identities, those kinds of things where we would had to simplify them or apply them like we did over the in the week in review, right? Okay. Polar equations. So converting from one mode into the other, so converting from rectangle into polar or vice versa. Okay, being able to convert equations from one into the other, and vectors. So that's what we covered. Identities, equations, and vectors, and polars.
Oh.
Okay? Questions? Yes, sir.
Are we meeting downstairs again?
Yes, good question. We'll meet downstairs. Now, one other thing before you go. I haven't looked at your Desmos activity since yesterday afternoon when y'all were in it. But this problem right here was the very end, and I really, let me see if I can give you some, what I want. I could not figure out how to state how I wanted you to answer it so that I could get it graded, all right? Did you all understand what was going on with the question itself? Okay? Yes or no? Did you understand, did you watch the video?
Yeah.
Okay, so the video just kind of helped explain what was going on here. So this piston, right, is moving in and out, moves in a horizontal direction like this as this moves around in a circle. All right, and so therefore, as theta is changing, right, as theta moves, then x, which is our displacement, is changing. So x is a function of theta, right? X depends on theta, correct? Okay. So what I wanted you to do in this particular problem right here is I need you to come up with an equation using the law of cosines that represents this problem right here. And you can see that I have sides of a triangle. I've got 1.5 as one side, 7 as another side, and x as the third side, right? Okay, and I have theta in here.
So basically, we would just try to come up with the equation like the first law of cosines equation, like the one with A in it.
Yes, all
That's
right.
where you-
You just have to decide that, you know, I need it to be a function. Let's see, how do I want to put that? I want it to be, I tried to put it in there. I want it to be like a squared equals b squared plus c squared minus 2.
We just
BC.
basically plugging everything in, but we don't solve it.
Simplify it though, simplify it, right? Clean it up. So I don't want to see the squared number. I want the numbers,
Oh.
like, I want to know what the value is. And I want it to be the number equal to where the angle is on the other side. Okay, maybe y'all should write this down instead of putting your paper.
So basically, we're just writing out the
Unless
equation.
you've already got this answer already done on the slide.
So we're like,
So maybe you should get your paper back out, and write how I want you to answer it.
we're basically just like writing an equation and simplifying it, but not solving it.
Not on that, correct, we're moving to that, right? So I want it to be the simplified part on the left equal to the simplified form of the angle kind of thing on the right, right? It should have 3 terms. Yeah, it should have 3 terms, I believe, in that section. Then you come over here, and now I want you to
Solve it.
solve that equation for x, because because this equation using the law of cosines is just ends up being a quadratic equation, right? It's just kind of rearranged, but it's quadratic in nature. And so then when you get to this slide over here, I want you to solve that equation for x, right? Use the quadratic formula to solve the equation as best you can. Okay, it's going to still be an equation because I don't have it equal to anything, right? It's just rearranging it, x is equal to this, okay? And then when you do that, well, when you do that, it should line up with that function right there. Okay? That's what I want you to do. The equation that you find here, when you put that x equals here, it's gonna be x equals some trig equation, all right? And that equation actually looks like this over here. The little highlighted one. So hopefully yours will match with mine. And then based on that equation, then you just need to tell me, determine the total distance the piston moves in one cycle.
So just to be sure I heard you right, you said on, I guess it was 8. You said simplified part on left equals simplified angle thingy on the right.
Pretty much
Okay.
value, so constant equals the variables on the right. Constant on the left equals the variable stuff on the right. Clean it up and see if you can get it that way. Okay? This was a problem. This is out of our textbook, which is kind of fun. And then I was all excited because I found that little video to help explain what the heck was going on with the thing, right? And I was showing it to my son because he came in town this weekend, and he said, "Oh, cool! I've got a problem like that in my homework too." They were doing it a little bit different, but it's pretty much the same kind of problem. And I don't know what he was doing, but he was doing it. So there you go. This is like a prelude. I said we were doing it with the law of cosines. See if you can get that question answered. I'll be happy to answer any more of that if you want. All right, so please study hard. Looks to me like you need to go practice some problems, right? You should be practicing the problems that I've given you. So we're done with trig tomorrow, and then we move on and cover, we go backwards and we talk about polynomials and rationals. Right, so if you don't have any questions, I'll see you tomorrow downstairs.
There's gonna be, are we gonna be able to have another part